It's not just the surroundings, it's not just the infrastructure what we have here. It's the people, the hospitality, the way they look at you, almost like family members. The food is great. For a South Indian, nothing better than what we get in BEGH at IIT Madras. And it's not far away my workplace. It's just 3 minutes walk, and it's a fantastic experience, not getting strained at the same time, feeling almost at home with the people who are looking after us in the guest house and the administration which is encouraging me to be a part of IIT Madras.
Hello and good day to everyone. Thank you for joining us today. On behalf of the Office of Global Engagement, it is my pleasure to welcome you to the 57th webinar from the IRIS webinar series. My name is Richu George, and I'm a part of the Office of Global Engagement at IIT Madras. The Institute of Eminence scheme was launched by the Government of India to empower higher educational institutions and help them become world-class teaching and research institutes. IIT Madras is proud to have been selected as one such institute of eminence. A total of 68 research initiatives belonging to 21 identified technology clusters are presently underway at IIT Madras. And as a part of these initiatives, the IRIS webinar series aims to showcase the innovative research being generated to various stakeholders like the students, researchers, industrialists, and policymakers. From the Advanced Manufacturing Technology Cluster, the research initiative presenting today is titled Additive Manufacturing, led by Professor Murugayan Amirthalingam. Additive manufacturing, popularly known as 3D printing, is set to bring a paradigm shift in engineering. This webinar is aimed to provide how AM can be used to produce end-use components with newer materials and improvements in performance. Now, to introduce Professor Murugayan, who is the principal investigator of this research initiative, Professor Murugayan is an assistant professor in the Department of Metallurgical and Materials Engineering Department of IIT Madras. His research interests include additive manufacturing, welding process development, welding metallurgy, and alloy development. He is currently guiding 12 PhD students in the areas of additive manufacturing and welding. He is a member of Technical Management Board of International Institute of Welding, representing Asia, an invitee to the joint meetings of Japan, Korea, and China Welding Societies, Chairman Technical Committee at the Council member of Indian Institute of Welding, a national delegate and expert member of the Technical Commissions of International Institute of Welding. He has published so far 40 journal publications, a book chapter, and holds 2 Indian patents. He has so far received 4 awards for his research accomplishments, including the Kenneth E. Sterling Award from the International Institute of Welding. Thank you for being with us today, Professor Murugayan. Now it is my pleasure to introduce the moderator for the webinar today, Professor Sundar Vedanarayanan Atre. Professor Sundar Atre is endowed chair of manufacturing and materials in the University of Louisville, USA, and the director, Additive Manufacturing Institute of Science and Technology. Dr. Atre is leading an effort to establish a new interdisciplinary program on digital manufacturing and design at the University of Louisville. Dr. Atre's current research in advanced materials and multi-scale manufacturing focus on additive manufacturing and powder injection molding of metal and ceramics. His research group, the Materials Innovation Guild, has generated over 200 publications, 7 issued and licensed patents, and over 20 intellectual property filings. Professor Sundar has received numerous awards for his academic achievements, including Molding Innovation Day Award, UFL Partnership Minority Business Development Alliance Award, Louisville Additive Manufacturing Business Development Alliance Award, etc. Now, thank you for joining us today, Professor Atre. We're very excited that you could be a part of this session. We also have a very distinguished panel with faculty from across various departments at IIT Madras with us today. We have Professor N.V. Ravikumar, Professor K.C. Harikumar, Professor G.D. Janakiram, Professor Kamaraj M., Professor Lakshman Neelakantan, Professor Manas Mukherjee, Professor T.S. Sampath Kumar, Professor Ravi Shankar Kottada, Professor N. Arunachalam, Professor K. Hariharan, Professor Ratnakumar Anabatula, Professor R. Jagannathan, Professor G. Saravanan Kumar, and Professor R. Velmurugan. A very warm welcome to all of you. Before we start, a note to the participants, please use the Q&A to enter your questions and upvote the questions that interest you so that the moderator can prioritize them later. Over to you, Professor Murugan.
Thank you, ma'am. I'll just share my screen. Is my screen visible?
Yes.
Am I loud and clear? Okay. Good evening, friends in India, and good day to those who joined abroad. So this webinar is aimed to give what is actually going on in additive manufacturing field in IIT Madras. Rishi Madam already explained about IIT Madras initiative about setting up centers of excellence based on the Institute of Eminence grants which we received from Government of India. So we, a team of faculty members across various departments in IIT Madras, formed this research group in proposed Center of Excellence in Materials and Manufacturing for Futuristic Mobility. So additive manufacturing is as which Madam said, is going to provide a paradigm shift in manufacturing, especially in automotive and the bio applications. So we have been working on additive manufacturing in area in various levels, including fundamental research up to the product development for industries and strategic sectors. So we are now concentrating on taking the additive manufacturing to next level, what we call in TRL 6 and 7 in Indian context, by focusing on various research topics, which I'm going to cover in over 15 minutes or so. So as I said, I mean, we are part of the Center of Excellence in Materials and Manufacturing Futuristic Mobility. So that has about 5 verticals, and additive manufacturing is one of the verticals. So you may be seeing tomorrow and day after some of other webinars on other verticals in this center. And we'll be concentrating today on additive manufacturing. Okay, so before going into detail about what we are doing, I just wanted to give a quick introduction about what is additive manufacturing. So additive manufacturing is a new process which actually conceived to manufacture the end-use components directly from its design. So we take an engineering a component design and we slice it, and then subsequently we print the entire component layer by layer, so that we use the end-use components of the complex geometries and the problems that are associated with conventional manufacturing, like the machinability, castability, extrudability, and formability issues we may overcome by directly producing end-use components from the design data. So it refers to process of joining materials to make parts directly from 3D model data layer by layer. So the video I show over here in the bottom corner, where we have set up a facility in IIT Madras to print a component using a process called laser powder bed fusion system, where the individual layers are printed, what you will see in the video. Like in a conventional manufacturing, so suppose if you want to produce such a sphere, so we'll have to first cast a block, and then subsequently we'll have to machine it, right? So there is additive manufacturing. So we take the actual design of the sphere, we slice it, and then we build the entire component layer by layer from its direct data. So what are the 3 important attributes of additive manufacturing? So the entire manufacturing chain is automated, so fully automated process, and we generate the object directly from the design data, right? And because we actually print layer by layer, there is no need for part-specific tooling. So that means that the cumbersome tooling, what we require for in a casting process, or when you form a component using an forging, or by any other say deep drawing mechanism, we need a specific tooling. Whereas here we don't need a part specific tooling. There are various names given to additive manufacturing. For example, rapid prototyping, rapid manufacturing, 3D printing, which is colloquially people call this process, or solid freeform fabrication, direct digital manufacturing, and you may find it. But all the processes, what we actually call each names are referred to additive manufacturing. The conventional welding engineers or welding scientists, we get excited the moment we hear the term additive manufacturing, especially metal additive manufacturing, because there is direct linking between welding and joining. So the physics, what we understand from welding, we can apply. For example, here we are using a laser beam to melt the powder. So it is similar to what we do in laser welding, where we use a laser to melt and to coalesce the interface to form weld joint, right? And here we are also melting, and successive layer is actually welded with the previously deposited layer or previously melted layer. And so the physics of welding and joining can directly be used in this process, especially when you use laser and plasma-based heat sources to manufacture components. So why metal additive manufacturing? So there are a lot of advantages of metal additive manufacturing, what I show over here in this slide. The biggest advantage is the materials energy saving. So I see one component over here. So this is an automotive component used for an electric vehicle. So to produce this component in a conventional manufacturing method, so the actual net weight of the component is about 100 grams. It's made of aluminum, right? So when we want to produce by conventional way, we need to forge it to sort of a rectangle block, and then we'll have to completely machine to realize this component. So we start with about 250 grams of aluminum block, and we waste about 100 grams to realize this component. So it leads to a tremendous amount of material wastage in terms of chips, and the energy consumption in various processes, including forging, machining, will be tremendous. To realize such a component in additive manufacturing, so from this STL file, for example, and we can directly print such a component. So that leads to the large amount of materials and energy savings. And the second is the design freedom. So here, because we print a layer by layer, the smallest feature what we can print in the previous image I showed you in the video in IIT Madras equipment is about 200 microns. So we can realize complex designs in this process, which are otherwise not possible by conventional way. You see here, these are cellular and architecture designed components to exhibit various properties like oxidic properties, or to have good heat transfer for heat exchanges, for example, and to effectively strengthen the material so that the engineering performance of the component can be increased by carefully modifying the design. So such a complex design containing components, again, it's very difficult to produce by conventional manufacturing. The third advantage is the timely and the customized manner we can print these components, especially it becomes very critical in healthcare industries. So one of the projects we do as part of this center is also to produce a maxillofacial reconstructive implants using very new alloys, which are aimed to generate methodology to print such complex implants in one go moment the patient's CT data is available, right? And the other advantage is, again, we can redesign the engineering components effectively to enhance its performance. For example, this is a die punch used for an open die forging. And the life of the die is actually, depending on the effective heat transfer and the wear resistance at the surface of the die. And we can manipulate the internal cooling inside the die, which are actually not open to outside. So therefore, the performance of the dies can be improved. And we can also locally change the materials. When we print a couple of layers, or some part of the component can be printed using different materials. What we call it functional gradation, right? So that is also really possible. Then the repair application. Some of the additive manufacturing processes, for example, direct energy deposition using a laser or arc plasma, where we can also refurbish the component by depositing layer by layer by different materials. So the life of the component can be enhanced for efficient engineering use. So we have been working on that, the repair and refurbishing also for various strategic industries, also on components used for automotive applications and power generation applications. So to summarize why additive manufacturing, so it would lead to reduce, reuse, and recycle talisman. So that's what we are aiming here in IIT Madras to effectively implement these three words. And apart from that, it will also lead to a lot of material innovation, because the alloy development is primarily determined by the ability to manufacture. So, for example, if an alloy shows excellent engineering, service condition in laboratory scale. It exhibits good properties when you test laboratory, but when you want to scale up to manufacturing, it is very difficult to produce component using this alloy. So therefore, those alloys are not really explored for various applications. So here in additive manufacturing, so the problems associated with forming and manufacturing, it's not there. So therefore, we are trying to invent new alloys where we can also use those new alloys for engineering components, which show excellent properties in laboratory scale. Again, on-demand customization manufacturing, last-minute change in designs, we can also get it up. So therefore, it is actually going to make manufacturing simplified. Okay. So what do we do in IIT Madras in this area? Just to give glimpse, and I later, we can also discuss. If some of you are interested in doing some of this, making partnership with us in this region. So one of the important activities what do is development of novel high-performance engineering materials by looking at a new combination of alloys for engineering applications. And these alloys cannot be produced by manufacturing by using conventional manufacturing. So we are aiming at bringing a plethora of alloy composition into a system, and then design for additive manufacturing. We can remodify or create new novel designs with an enhanced performance. And then we are also working on process innovation to develop a methodology to effectively produce components, to understand how the process affect the microstructure, and to avoid the process generated anisotropy in mechanical properties. And we are also working on post-processing methodology, especially some of the additively manufactured components, surface finish, how we can improve it by developing new novel surface polishing, including electrolytic polishing, magnetoreological polishing, etc. And then development of novel structures, architected designs, lattice structures, sandwich panels, metallic forms, and these are widely considered for lightweighting of automotive component, also for biomedical applications, right? And we are pushing ourselves to also invent new components for futuristic mobility and bioimplants, or a couple of components I showed you in earlier slides as well, which can also lead to lightweighting and improvement in performance. So this slide summarizes the various activities and sub-projects we do in this research group. So we are focusing on the 5 important verticals of IT manufacturing spectra. So the first is the alloy development or new material development, including high performance ferrous and non-ferrous alloys, and to develop feedstock to print polymer derived ceramics, and then to develop methodologies to print multi-materials. Say, for example, I showed you a forging punch. The majority of the part would be printed using a conventional low carbon steel, whereas the regions where we exposed to high temperature and strain, we can also introduce the high temperature materials or various materials. So therefore producing a functional gradation, right? And so one sub project is also on electrospraying of feedstock powders, where we can use a new technique called electrospraying to print, to produce powders for additive manufacturing. Then the second component of our research is on design for additive to develop lattice structures and oxidic materials and sandwich panels. And we arrive at new novel designs, and then using additive manufacturing, we realize and test those designs for automotive and bio applications. Then the third is the process innovation side. And some of us are also working on hybrid processes. So for example, combining the additive manufacturing with machining, not only the simple CNC machining, and also to use rolling to introduce compressive stresses, and using an ultrasonic impact, so to mitigate residual stresses, right? And then we have been extensively also working on numerical analysis of IT manufacturing process, especially to minimize distortion and anisotropy during printing, which is one of the biggest problems here, and also to optimize the powder behavior in a powder bed system and the powder fed direct energy deposition systems. Then the 4 of us are also working on post-processing methodology to develop novel methods to polish the AM component, including plasma-electrostatic process polishing, vibrating magnetic abrasive polishing, and chemical abrasive floor polishing, etc. Then the fifth important vertical is to push the additive manufacturing to an implementation level to develop applications in automotive, aerospace, healthcare, and tooling industries. So one project, what I talked about, is on developing processes and facial implants using additive manufacturing for timely and customized healthcare, and the metallic foams for various applications, including hypersonic vehicles, right? And again, I talked about the dies and tools with an efficient heat transfer and stress relaxation design, and as well as the lattice structures used for lightweighting applications. So what are our objectives we are working on here? To develop new alloys and materials for commercial use in additive manufacturing. So that's our primary objective. And then to design and demonstrate prototype components with efficient design for ranging engineering and healthcare applications. And also the process innovation, including the hybrid processes, post-processing methodologies for accelerated industrial adaptation of additive manufacturing. And then we are also working very closely with a lot of industries, some of the partner industries I'll show, to implement AM technology in aerospace, automotive, and the bio applications. So this is our team. You may kindly note it out. And for more information, you can also visit the website of ours. You can Google additive manufacturing IIT Madras. That will also take you to this website. So we have about 14 professors in IIT Madras across 3 departments: aerospace, MME, metallurgical materials engineering, engineering design, mechanical engineering, covering all the 5 verticals I talked about in the earlier slide. So we completely cover the entire process chain in terms of academic research and implementation. And we also have a large number of collaborators identified. Professor Sundar Atre, one of the distinguished research scientist and academician in additive manufacturing, who is the moderator of today's session. And he is actually in Mr. Louisville. We set up one of the best centers of additive manufacturing in the world, and the other centers across the globe for additive manufacturing, including University of Wollongong Center on facility for intelligent fabrication. And apart from that, we have a wide range of collaboration across the globe. In various countries, they are actually collaborating with us on these important and advanced topics. We find that interdisciplinary research is important to take the additive manufacturing to next level. So some of the industrial partners are listed over here, and we have a joint collaboration research right now going on with Super Auto Forge. So one of the world's largest automotive forging companies, and the Intec Additive, who are actually suppliers of our equipment, and L&T, Fronius, Lincoln. They are primarily into welding-based additive manufacturing techniques, primarily arc plasma-based wire arc additive manufacturing, and Indo-MIM, one of the leading powder manufacturers, and Carbonatum Universal, mainly for ceramics-based additive manufacturing. And we welcome, even other industrial partners if they want to, take part in some of the research what we do and implement additive manufacturing in their facility. And what we have right now, we set up 3 important facilities for additive manufacturing. So one is the laser powder bed fusion system. It just got inaugurated day before yesterday, on Thursday, sorry, by our director. So this is a laser powder bed system with a build volume of diameter and height, which can print any metal powders, alloy powders, which can be welded. Okay, so that's a thumb rule. Technically, the alloy based in additive manufacturing, if that alloy is weldable, then we can also print it, right? And apart from that, we have in-house manufactured microplasma based wire direct energy deposition system, which cannot be used. It cannot be used for building slightly larger volumes. And we have a large volume additive manufacturing facility using arc plasma, where we can also print components like impellers, what I showed you in the first slide, which we attempted for our meeting. Good. So what we want to bring in terms of societal impact, and we want to create an ecosystem in the IIT Madras to set up or to facilitate the sustainable development for additive manufacturing for industrial use, and which can also give us methodology to produce implants for affordable and timely healthcare, And also we are actually working towards creating the processes for war victims and veterans to facilitate the rehabilitation. And we have done quite a bit of work on repair of ancient sculptures and idols using multi-pass deposition using DED. And we did a couple of very important work, which we feel that it's one of the area where we like to protect our national heritage, especially the old Chola bronzes, to repair them using additive manufacturing. And of course, we are also working towards developing systems for printing components for disaster management, especially a country like us, to face. Suppose if one component is required urgently, we can just print it and then use it for, say, power generation. And we are also aiming to develop skill development workshops like what we are doing it now to introduce, as well as hands-on training workshops, which we will be planning regularly. You will also get announcement from our GE office when we plan such that, so that now we can improve livelihood for this technology, where we see that IT manufacturing can democratize manufacturing, where if someone wants to produce the end-use component, it can straight away using the equipment can be printed. So what we can offer for the participants, say, of course, industrial consultancy is always there. And if someone wants to print a component, the methodology, how to print, and we can also take it that. And short-term training and hands-on workshop, we have been organizing quite a few. Keep watching us in our web pages, as well as newsletters from IIT Madras. And we are also planning to launch a new MTech program online on IT manufacturing, and we are working on towards that. And of course, testing and qualification of AM components. So that exercise, we are also partnering with International Institute of Welding to qualify the components for IT manufacturing in that. So with this, I wind up my talk, and we'll be glad to take up questions. And if you have any in the question and answers, or feel free to get back to us. Thank you.
Thanks,
Richu, over to you.
Murugayan.
Yes, Sundar.
Yeah, so Richu, can I step in now?
Yes, please. Yes, Professor Sundar.
Yeah, thanks. So a lot of interest in the Q&A and from the attendance as well. So thanks for the overview, Professor Murugayan. In grouping the questions that are given, can you hear me?
Yes, Sundar, I can hear you. Go ahead.
Okay. So when I lump some of the questions together, they follow certain themes. One is related to just performance attributes of additive manufacturing. What kind of precision you can get, what kind of properties can you get, what kind of surface finish can you get? Can you address some of that?
So again, the surface finish is a function of what process we are going to use. Yeah, Sundar, you can also pitch it up. Like for example, when you use a laser powder bed fusion system, the surface finish, what you're going to get will be better than when you use a powder fed base direct energy deposition system. But some applications we don't need such a good surface finish. For example, the impeller I showed you over here, it is a very simple design, but it's large volume, so we can always machine it. The post-deposition machining can also give us a milling finish. So that is depending on what component we are going to get, we are going to use additive manufacturing for. The other is the properties. So again, I showed you one of the boxes we showed. The mitigating anisotropy in mechanical properties is a challenging one. In data energy deposition, we did the considerable amount of work on getting a uniform mechanical properties. Again, it is a function of how we can understand the influence of the power source on the evolution of microstructure. That can be also negated. Yes, Sundar?
So then the next set of questions relate to manufacturability, productions, volumes, dimensional constraints, costs.
Yeah, so again, so when we use a powder bed based systems, the volume of the component what we are going to print is limited based on the bed size what we are going to use. Like I said, in our facility, we can print 150 mm diameter, 180 mm height components. When we use the DED, like what I showed, arc plasma DED, we can produce a large volume components, even meters. Like we attempted impellers for strategic applications. We could print about a meter overall length based on the impellers. So depending on what process we are going to use and the design of the component, simple and large volume components, we can print using a DED based process, and complex and design containing components, we need powder bed based systems for alloys. Yeah.
Thanks, Professor Murugayan. The other set of questions also address aspects related to reliability and standards relative to other manufacturing options that exist.
Yeah. Sundar, thanks. We have formed already one working group in International Institute of Welding on standardization, which I'm also part of it. I'm sure there are some efforts in US as well. Can you also comment the qualifying additive manufacturing components?
Another area is materials utilization. Yeah. Can the powder be recycled? Yeah. And in that same vein, how do the powder attributes and what's different relative to powder metallurgy in the conventional sense? That's in center, I imagine.
Yeah. So that we use the powder-based processes equipment, we could make use of 70% of the powders to make 30% goes as a waste due to part growth, also due to the fume formation. So the powder which got agglomerated, they will have to be recycling it. As of now, that is one area which we can also explore recycling powders. Maybe Ratna, can you also comment on how we can enhance the usage of powders by combining stimulations and modeling and optimizing powder spread?
Sure. So the most of the mechanical properties that you can get out of this powder bed based additive manufacturing process depends on how good is your powder bed prepared. For example, if you are having powder spread over the bed and you want to have uniform distribution so that everywhere the material composition is uniform, so that the output what you are going to get is also what you expect. So in order to do that, can we come up with the simulations wherein particle-based simulations, which will allow us to design the powder spreading strategies to obtain a uniform or whatever designed composition variation throughout the bed, so that we get what we want rather than what we get what we depend on. Simply, we can influence how the powder is going to be spread at various locations and then be able to decide the quality of the product. In addition to that, one of the major issues with the cost issues with respect to the powder bed manufacturing is that the particles are usually expected to be spherical in nature, but then from the simulations, one can find out what are the conditions under which you can actually work with non-spherical particles and then be able to get the same kind of quality, if at all it is possible. These are the kind of things that we can address through the simulations.
Thanks for the clarification, Ratna. And now the follow-up questions pertain to where can we use additive manufacturing? When do you use additive manufacturing relative to other options in manufacturing? And if you can also highlight what are the opportunities for additive manufacturing for a small manufacturer?
Yeah, so additive manufacturing, I already covered 4 impact and aspects to reduce material and energy and timely healthcare, what we see, and the design innovation to improve, like for example, CO2 emissions in in terms of light weighting. And we can first identify some low-hanging fruits, what we have been also advising industries to identify, where the IT manufacturing can bring a considerable amount of all these four important efficiency in world. So therefore, definitely to bring new materials into the system, which are otherwise not possible to manufacture, and to reduce the material wastage. So we have done another white paper also when I showed you on aluminum, especially in titanium. When we replace using conventional manufacturing, IT manufacturing, we could save about 90% of the material. So in terms of using new materials and the materials saving, definitely, and to enhance the life, and what we find by simply moving from conventional manufacturing, actually already due to the control over microstructure, where we can implement layer by layer, the performance of the increases significantly. One case study is again the forging die, like changing from conventional to additive manufacturing. We could enhance the life from 8,000 components to 12 to 13,000 components. So 1 hour shift to 3 hours shift, we could get it just by printing the die using additive manufacturing. So again, so opportunities are there, and we'll have to just in India explore the use of AM to make it to next level. Yeah, Sundar.
The next question, Professor Murugayan, is, can you provide some examples of materials that cannot be manufactured by additive
by conventional way? So again,
or no, that are normally used conventionally but cannot be manufactured by additive manufacturing.
The new alloys, exactly. Sure. So one name alloy component we just developed reconstructive implants. This is based on cobalt, chrome, moly, iron. Okay, so this system is it's very difficult to machine this alloy, but it shows excellent biocompatibility as well as the corrosion resistance. And it's also, we are reducing the amount of cobalt added this so that it becomes cheaper. And because of that, we can't use this alloy for making implants because it's not possible to machine. And we could show that by using this alloy, we can also achieve a low cost because we're reducing the amount of cobalt. And by not machining, we just directly print the implants. We can also save the time required to manufacture. So this is the classical example of how additive manufacturing can bring the change what we discussed.
What about the reverse side? Are there things that are difficult to, the other alloys that are difficult to fabricate by additive manufacturing that can be easily made by other techniques?
Yeah, exactly. Okay, so reverse is also a very, very important question. What we see at thumb rule, especially the metal additive manufacturing, any alloy that can weld it, that can also be printed. Okay, so the alloy which show the poor weldability, especially in aluminum, if you say 6,000 series, we always have a problem with hot cracking. And additive manufacturing, is nothing but, the welding, right? So hot cracking issues of 6,000 series should be, carefully manipulated when you print. And some of the tool steels what we use for forging tooling industries. So those are also very difficult to print, and requires extreme modification in process so that we can print those components as well. Yeah, using those alloys. So that.
Next set of questions relate to design and applications. So how is design different for additive manufacturing? How do you select components?
I think the best person to answer is Professor Saravana. And design for AM.
Yeah, hello.
Yeah.
Yeah, hi Sundar, and
Saravana.
Yeah, so from a design perspective, the complexity of the design is one thing that an AM process can handle, whereas the conventional manufacturing process, it is very difficult to make complex topologies by machining or other tool-based processes. So that is one sure advantage that could be exploited, and that is where we see the creation of various topologies like cellular architectures that are being used in lightweighting or for energy absorption or various other applications. And the other complexity that one can think of is the material composition complexity as well. So it is not only geometric complexity, but also compositional variation or functional gradation. So designs can exploit these two attributes of AM, and people can disruptively think of making new designs. The other consolidation of the components. In conventional way, we have to make several components and assemble them. So precise assembly, the assembly tolerances, the errors that happen, and the rejections, all of this can be avoided because we can make components as a monolithic structure, as a single component. I think these are some aspects that I think the panelists, others can also comment.
Thank you, Professor Sarvana. I would like to thank Professor Murugayan because he has to catch a flight to come to Chennai. He's in Bangalore right now. But we have the rest of our panel available to continue answering some of the questions. We have 3-4 more questions if others in the panel can be around to address some of these as I group them together.
Yeah, thank you, Sundar. Thank you, team. See you then. Bye-bye.
Have a safe trip.
Professor Murugan, thank you.
Thank you. Bye-bye.
Bye.
So I think Professor Saravanan, that was an interesting set of introductory concepts that you provided. Can you talk a little bit about what kind of support services IITM can provide in terms of design help for those interested in evaluating components for production by additive manufacturing?
Yeah. So from a design analysis, the conventional way of CAE can be again used in the case of AM components. I think there was a question on what are the differences or what kind of analysis needs to be undertaken for the AM components. The design for additive manufacturing needs to consider the buildability of the components, because in metal AM, when the components are being built, the failure can happen, the build failure can happen if the distortions are high or the support structures can because of the heavy built-in stresses. So one can avoid these by suitably simulating them and adjusting the process parameters. So we do have competence in doing such analysis so that the buildability of the various designs can be addressed, or we could simulate them upfront, and buildability of the AM components can be predicted, and we can give optimum process parameters or support structure design. That is one aspect from a buildability of the AM components. From the perspective of creative design, there could be support in terms of say creating novel designs using concepts like generative design. So that is one area where we could again help industries to look at their problem, the component design or the product design that they are looking at, and we could help them in achieving newer designs or complex designs.
Thank you, Professor Saravanan, for that clarification. On a similar note, a lot of questions related to needing reassurance on material properties and so on. What kind of support can IIT Madras provide with those who want to enter the manufacturing in this area in terms of making sure that process-dependent or design-dependent flaws can be addressed at an early stage while planning for production. Maybe Professor Ravi Shankar, you might be able to elaborate on that in terms of testing services and so on, both from the material side as well as production side.
Yeah, it's Sundar. Am I audible? Hello.
Yes. Yes.
Yeah. So we have already formulated guidelines for others to access our facility. As per the proposal and after the machine is established, we are opening this facility for anybody within IIT Madras other than the members of the Additive Manufacturing group to access at least 1 day per week or a few hours per week. That's one for the institute people. For outsiders, they can approach through the ICSR, Industrial Consultants and Sponsor Research, where we can identify if the customer comes up with a problem of the specific problem, then we can discuss it and then we will come up with whether it's possible and what way we can actually take up that particular project. For example, recently we have signed up an MOU with one particular automotive ancillary company where they have come up with some 5 to 10 different materials and the components, and we are trying to address their issue one by one for one and a half years like that. So anybody can access the email addresses, and that way we will be able to provide depending on the case-to-case basis, essentially. Yeah.
Thank you, Mr. Ravi Shankar. Now, if there are other specific questions related to individual needs or concerns, is there a website or is there a point of contact that people can relate to and reach out to? Because that would help in some of the very specific questions that were not answered in this Q&A. I think, Ravi, you're muted.
Oh, sorry. Yeah. So you're saying that, I mean, you want me to answer something specific, any specific questions related to
if
that?
Someone wanted to, if someone had to reach out,
okay,
is there a point of contact we can provide?
Yeah, that is Professor Murugai and Amrutalingam or any of the faculty who are involved in this. So the IOE website, which Murugai has provided in the initial slides, that will be the point of contact. Yeah, they can approach directly to one of us. Yeah.
Thank you, Professor Ravi Shankar. I think I've gone ahead to provide the email contact again to everyone on the chat for those who have further questions. At this point, let me turn this over back to Richu.
Yeah, thank you. Thank you so much, Professor Sundar. It was wonderful to have you with us today. You went through in such detail through the Q&A and directed so many other questions towards the panelists. And clearly, there's still so many questions coming. People are really invested in this. So thank you so much for spending so much time with us. We know you missed your routine changed a bit, but thanks a lot. Thank you to everyone on the panel for answering all the questions, especially to Professor Murugan, who had to do this webinar in between his flights. And thanks to all the participants. We really enjoyed having all of you here today. Thank you. Thanks a lot.
Have a great evening.
You too, sir. Thank you. Thanks, everyone.
Thank you very much, Professor Sundar, for being part of this and helping us to reach all of us.
Yeah, thank you. Thank you very much.
Thank you all for participating, all our Additive Manufacturing team at IIT Madras.
Bye.
It was great to see the IITM team again.
Good luck to the team as well.
Yeah. Thank you, ma'am.